So this is Jakub presenting structured arrays with algebraic shapes. Please take it away when you're ready. Thanks.
Thank you. Like this. All right. All good. Right. Thank you for coming to my talk. So my name is Jakub, and this is a paper co-authored with my supervisors, Dominic and Mycroft, as part of my as a part of my thesis at Cambridge. And all right, let's get started. So as a quick introduction, static type systems are great, and we want more static type systems. You get guarantees, and you get essentially documentation of library interfaces you write, and the programmer can write better abstractions following types. But for array type systems, or for array languages, there isn't really sort of maybe a favorite typing discipline. And I would argue even that there's you end up with these two extremes where a lot of will be essentially untyped, or there will be very little type information, or people will immediately start going towards the extreme of having dependent types in their language. So, so why might this happen? Why this polarization in this sort of area of array type systems? And I think this is to attribute to that there isn't quite enough nuance to what an array is, as a value, and thus there's not enough to say about its type. Because a lot of libraries, like the ecosystem, sort of sticks to n-dimensional arrays in the style of Fortran, and maybe has 3 dimensions, has some specific element type, and then maybe there's 2 different ways where you can really write down what the syntax of array types is, where you might think of them as it's a scalar or a vector, which is another array, or it just has a specific rank. But what can you really keep track of is the element type, and then maybe the number of dimensions. And even the number of dimensions with some array primitives might end up being a bit crazy. And here, I think what you quickly converge to is you want to keep track of sizes of specific dimensions, because maybe operations they're using depend on sizes matching, or you want to index and you want to know that your indices are always in bounds. So quickly, these non-trivial type systems will end up growing dependency type, sort of carefully limited dependency type extension, like in Fulvark's case, or you have entire designs like DEX, where it's mostly about a dependent type system. But that's maybe not ideal. The part of the reason why you're getting these dependent types is size arithmetic. So you get primitives like, flattening arrays, like a matrix, you want to turn it into a vector. You want to concatenate a pair of vectors, and then you quickly get sums and products of sizes. And now you want these dependent types to keep track of these this arithmetic, and you get these expressions, and maybe you want a solver to figure out whether sizes are equal or if they are bounded or stuff like that. And this just adds this computational complexity and complexity for the programmer themselves, because the system becomes more complex, less predictable. So in practice, a lot of practitioners would just end up using untyped programming. You don't if they're using Python with NumPy or PyTorch, they're trying to write down type annotations. They're really doing their best, but they don't end up doing a lot. And then maybe a lot of these research languages will have these dependent types, but maybe it's difficult to extend these in existing systems. And then even if you do put dependent types in your system, you still have these other sort of problems like existential sizes, or do you have jagged arrays in your system? Can you even write that down as a type, or is it just illegal? And maybe size polymorphism, where if you keeping track of sizes as sort of part of the type, then now this has a computational content, and this makes your system a bit more complex. So what can we do about this, and how can we address this? And I think what I sort of look towards is these generalizations of what array structures can be. So more than just n-dimensional arrays. And 2 particular sources of inspiration for me are labeled array axes, which come up in libraries this is from the Python ecosystem. One is called named tensors, sort of labeling dimensions of arrays, and another one is xarray. And another one is Napierian functors, which is this idea to generalize what an array as a container is. And this is explored by Jeremy Gibbons with array programming and applicative programming in the paper. And so where I go with this is to look, maybe look towards more functional roots, to think about what works really well with functional languages, which is algebraic data types, and avoid dependent types, and then also look at more recent developments with type inference with subtyping. And we can sort of combine the two, because we can get type inference for these sort of structural algebraic data types like records and variants, and we can sort of endow it with subtyping. And here I follow Stephen Dolan's algebraic subtyping, or this sort of direction of this sort of seminal development. And the sort of key idea, the approach here, is to have structural record and variant types for shapes and indices of arrays. Or sort of vaguely like that. This is the vague idea. And then I equip it with subtyping and argue that this gives us interesting patterns, that this models interesting array programming patterns and stops you from making indexing errors in particular. All right, so the key ideas here. So introducing star. Star is this calculus that sort of develops these ideas formally. And it's a functional and pointful array calculus. Pointful here just ends up meaning that we focus on array comprehensions where you define the shape of an array and then we say what is the element at each index. Like the elements of this array are given in terms of like a function of the index. And then arrays can obviously be indexed with an arbitrary expression and they can be and their shape can be recovered with an operator. And as I've said, as I pointed, shapes and indices are special. They're structured types. And besides the obvious, like you want arrays that can be indexed by integers because that's what arrays sort of are. You want to give them more, you want to make them, don't make them flat. You want to make them nuanced. And there are two pieces of nuance. There's product shapes and concatenation shapes. And these are respectively indexed by records and variants. And they're sort of denoted with these funny braces that sort of are similar to the corresponding standard notation for records and variants. So let's start off with looking at records. Like, why is it interesting to index your arrays with records? So for like a bunch of axis labels and existing shape types, we'll have a product shape, and this can be indexed by records of a corresponding record type. And here we'll say that this record can have more fields. So what this means, if I write down, for instance, like a series of RGB images with like 3 channels, I can write down the shape of an array which stores that. It's a 4-dimensional array. So if, normally I will just have a 4-dimensional array which is like 132, 32, 3 in shape. Here I can label these axes and then I can index them with a record. And a fun thing I can do is that this record I index with can contain extra information. It can contain extra dimensions in the index. And for instance, here I added a dimension called depth, and it doesn't matter. This information can be ignored when I ignore. And this is used, how we sort of leverage subtyping in this system. And you can notice sort of special cases like if the array has no dimensions, it's a product with no dimensions, then it's in particular, it has exactly one element because you can index into it with an empty record. Now you've got variant indices as well, and these are also fun because if I think about, okay, I'll write down like a concatenation shape, so I'll write down a bunch of components, I'll say I have a left, center, and right component. Then the way you index with a variant type, so like a tagged value into an array of that sort of shape, this corresponds to selecting one of these components, like left or center, and they specify the index within the component. So maybe I index into center 4, so I index into the center component with the index 4. And again, there's like a nice special case, which is the array of shape with an empty concatenation shape. The concatenation that has no components is the empty array. So again, concatenations and variants are sort of connected in this way. Okay, so now you can make more complex structures out of this as well. So it's not just that I can make a product of like integers and there's a size sort of shapes and concatenation of size shapes, but I can have products of concatenations. So for instance, I can sort of refine the type I use for RGB, for RGB images. I can say that instead of saying that the channel dimension is of size 3, and then arbitrarily say that maybe channel 0 is R and channel 1 is green and channel 2 is blue, instead I can label these as part of a concatenation shape with appropriate sort of singleton cases, because like there's no more information within except which tag it is, whether it's red, green, or blue. And then I can index into this with something like row 15, column 17, channel green, right? So that gives me this nuance that before was missing, that before you have to keep in, knowing that, for instance, the size of a dimension is exactly 3 and the order between the different dimensions. Now it's sort of labeled and it has this extra structure to it. All right, so like here's a summary of sort of what this ends up developing to. So we've got sort of size shapes, product shapes, and concatenation shapes, and you've got some different examples. And what's sort of interesting to notice here is that product and concatenation shapes behave like records. Like up to typing, like you specify like what each dimension is, what each component is, and they essentially just behave like records. You can also project the individual components and dimensions. But what is special is that concatenation indices behave like variants. And this introduces like this funny complexity to the system where at some point you'll have to be able to sort of relate that, oh, I'm like trying to index into a variant, so I'm expecting a concatenation shape and not a product shape. And that's the general gist of it, of what types and values there are in star. But there's one more thing still to do, and that's one more key idea to star, and that's broadcasting. And rank polymorphism is great. It allows you to write more concise programs. And you might have this question of like, how can we generalize like rank polymorphism to this idea of structural shapes? And I think it works out quite well. And it still also corresponds to this idea of like having subtyping in the language. So when we have like NumPy style broadcasting, we'll have like funny things like if I have like three-dimensional arrays and certain sort of sizes are considered like, certain axes are considered to be not present and can be repeated along that axis, then an analogous sort of phenomenon will apply to product shapes, and also one can be done for concatenation shapes. So what we'll say is that broadcasting of compatible shapes will yield its least common subshape, and subshape in the meaning of like what indices are contained in both shapes, or like either of the shapes. So I'll give some examples of this to be concrete. So the first example will sort of show us that, okay, if I try to broadcast two shapes, which maybe are, again, used for like specifying images, so one is only gives rows in a channel, another one only gives columns in a channel, and if I broadcast the two of these, then the common axis, which is channel, has to be sort of assumed to be equal in both of these shapes. This means that the shapes are compatible, but row and column are sort of propagated to the result because they only occur in one of these. In more general terms, what you can do with this is give like more point-free primitives for star, and these sort of rely on broadcasting. And I will say that, for instance, if I want to define an element-wise addition on like a pair of arrays with these structured shapes, then I will say that the shape of the resulting array will be the broadcasting of the shapes of the two original arrays, and then I will add things element-wise. I'll just like take X. And the reason this works out, the reason this makes sense is exactly because of subtyping, because the broadcast shape will only give me like more specific sort of subtype indices, and this all sort of works out. Cool. So, you know, where does star shine? Where do things go well? Like, what's an elegant example? So the example I like is padding. Because padding has always threw me off with sort of index arithmetic that rises and stuff like that. So we'll have a simple example where we're padding a matrix and we have top, bottom, left, right cells. And we'll put +1s at top. I think I did it the other way around in the example, but don't mind that. That doesn't matter. Either way, we're padding a matrix. And the way you do it in like an imperative point-free setting, and really in any setting which has unstructured arrays, where the only thing I can really say is that the input is a two-dimensional array and the result is a two-dimensional array, is I have to set up the shape, and the shape is going to be a sum of a bunch of components, like a bunch of these individual sizes, and then I need to set all of the values, right? But the way I can only access the specific parts of the array that I want is I need to find the index ranges, right? And I feel like that's deeply unfortunate, because like these index ranges are sort of arbitrary. It's like you say that a certain thing has index 0, like for instance the top will have like, the top left element will have index 0, 0. And why is that the case? Why is that so different from bottom right? So obviously there's shortcuts possible in this code, but they're just shortcuts. Like the general principle of how this code has to be written is like this. It has to sort of recover those index ranges. Okay, so we're looking at star now, and we're going to sort of leverage the structure of the problem. And the structure of the problem is that we're producing a palette matrix that has columns and rows, which is sort of like a product. And now within those, we have like the different regions. We have like a top, center, and bottom region, and left, center, and right. This leads us to writing down this shape in star, which looks at the shape of the original array and uses that for setting the center parts, for the center components of the concatenations. And we have these two dimensions, row and columns, and within those we have, you know, this exactly corresponds, like all of these possible cases of concatenations correspond to these 9 regions in the resulting array. And what's really nice now is now we're using records and variants. We're playing with normal things, and we can do pattern matching by constructing an array of this shape, and then we can pattern match what is in the row and column individually. And you can consider which cases we're in, right? Because if we're looking at the center, then we want to copy from the original array. And if we're looking at the top, then we don't care, we just return -1, right? And that's exactly where I think this all comes together. And this is a bit perhaps verbose, but the nice principle is that I think this is way more maintainable and way more obvious than writing down a bunch of index arithmetic and saying, oh, this range is from t to t plus l, and now guess whether that's right. Obviously no, because we're mixing t and l, but you know, I feel like this is way clearer on like what information is actually being used. Okay. So I'll sketch the formal development of what comes up when we are like arising with star, because now you've seen that perhaps it is worth like developing this idea because of how products and concatenations naturally arise in like these very basic problems. So for operational semantics, it's like maybe a little non-obvious, but no, because I've said that we can index into arrays with sort of redundant information, there's this notion of like, what should an array store in terms of elements? And here like is a basic example where I store like these 3 different positions, and when I index with a position with an index that has sort of more information to it, then I just ignore that information and find the corresponding entry that's actually stored in the array. For types, the types are also quite straightforward. There's a bunch of obvious things. The things in color are sort of more interesting. So we've got the record, variant, product, and concatenation types. And then we also got the array type. And I'm lying a little bit here, but for now, let's just sort of keep to the lie. But we sort of want to have an array type which says it has like a shape and then it has an element type. And what's nice about this setup is that multi-dimensional arrays that are regular are given by product shapes. So if I really want jagged arrays in my system, then I can have just a nested array type which says I'm indexed by integers, and then within me are arrays also indexed by integers of some, with the array being of some size that's not unknown. So we don't need any existentials or anything fancy like that. But now I have to clear up the lie about sort of the array types. So there's a little bit of nuance when it comes to giving this subtyping. So as I said, for shapes and indices, they just behave like records and variants. So this is completely standard. It's like textbook subtyping. But for arrays, it's like a bit unobvious because you probably want your shape to like also behave under subtyping, and you would want it to be covariant or contravariant. But as you can find in the appendix of the paper, this isn't like something that works. It's because indexing is contravariant, but accessing shapes is sort of covariant in the shape. So there's a trick that we can use where essentially we keep track of like a bound, like an interval in which the actual shape type must lie. This is sigma 1 to sigma 2. And then when we give the subtyping rule for arrays, it sort of makes use of this fact. And then we separately use the contravariant part and the covariant part of this bound for indexing and shapes, which is shown exactly here on this slide with these 3 typing rules, which are just the most important typing rules in the entire calculus. They're just saying that as we construct arrays, we like propagate the appropriate shape and index types, and then when we index, we look at the corresponding bound, the one that sort of makes sure the system is actually sound. But there's this funny thing here in red, which is the iota function, or it's a meta function, which is it's a function on types. It sort of takes an existing shape, and it will get the index type which is compatible with it. It's a type of all index types that are compatible with that shape. So there's this funny bit here, and one more funny bit to mention is that broadcasting is a bit tricky, but what is like an interesting property is that in most cases, because it is in a way a subshape, we can just look at the subtype of the operand shapes. So that's kind of an elegant bit that again connects with subtyping. Okay, so we now have to look at iota though, which is how do shapes and indices match? How do we relate them in the type system? And this is done for this meta function, and it's got a really simple compositional definition. Essentially, we look at the shape type or at the shape type, and we just replace all instances of the size things with the index things. So a product shape will be replaced by a record and so on. And maybe it's a bit weird to have this sort of construct in your type system, but it's actually like very reasonable. Like when we look at, like, for instance, Napierian functors, is the way they end up working out is they have this logarithm operation that says, if I have a container of this shape, what is the type of indices for this shape, right? And this is exactly what we're doing here. Analogously, there is an abstraction of containers independently type programming, and this one also uses something similar where we have a function on types, which given a type of shapes gives you a type of positions. Or a value of shapes gives you a type of positions. All right, so now with these things stated, because we know about typing and subtyping, we can say that star does actually have type safety. And the way you state that is just progress and preservation. But progress only holds up to integer indexing. Like at no point in the system did I ensure that integer indices always work out. What I can ensure is that there's a compatibility between sort of indices being structurally in bounds, that it's up to like those products and concatenations, but not necessarily up to integers. There's nothing in the system because that does sort of end up requiring dependent types. So, but I can end up, I can shell the typing. If I know that like shapes and indices match up to typing, that they match up to the structurally in bounds relation, and so indexing never fails. It only can fail at integers or sized shapes. And so where I can drag this further, and this is more conjectural, but seems to make sense, is that you can extend, so all of this was a star in a simply typed setting, and I believe you can extend star with parametric polymorphism and then design like a sensible type inference for it. And there is obviously this is something that would have to be worked out. I do have like a rough working implementation of this idea because it was part of a larger project on doing sort of design of structural subtyping and type inference with structural subtyping. But here, for instance, one thing that we have to take care of is this addition of the iota sort of type meta function. It turns out it's a homomorphism in the algebra of types, in the lattice of types. And this gives us nice properties that allows us to sort of work with it in type inference. And so there's at the bottom there's an example of what sort of type inference might we want to do. But maybe an interesting thing to note here is why would you want to care about sort of shape polymorphism? Why would you want to have polymorphic type inference for star? And I think what's interesting here is that if you write functions in star that never sort of index the input arrays at integers, and obviously you can never index the input arrays out of bounds. Like, you can only ever just ask the input array for its current shape and then like create an array over its current shape. But that just can't possibly lead to an index out of bounds because it only gives you indices in bounds if you're constructing an array of that given shape. In particular, they could all be structural. So either way, maybe that's not necessarily convincing, but I think it's definitely promising and it seems to work out in practice. Right, so I can start moving on to conclusions. So firstly, there's limitations to this system, and I've already hinted at this, that it seems algebraic subtyping and this approach of structural subtyping fits this very naturally, and it can be extended, but I can only test this with an implementation. So this is sort of a limitation of this work that has to be explored for the polymorphic case. Another case, I think, something that people point out to me is that they find the notation quite daunting. There seems to be a lot of different braces and funny dots in the paper. This is all because there's like 3 different record types and also a variant type, because products and concatenations and records, they're all really just records. And there is this nuance to them that are obviously different. They have slightly different behavior in different places. But maybe it's like a bit funny that maybe the design should be flattened to just say that this is all like record types and one variant, like one record type and one variant type. There's also the integer sizes that, like, I think this is more symbolic. I think you could, like, have integers be usable both as a shape as an index, but for technicality, this is how it's done in the development in the paper. There's also the question of could you embed this in like an existing language? Like it seems annoying to actually properly build like a new language based on just this specific one calculus. And I'm not exactly sure what the answer is here. I believe that with just, if you had like a proper implementation of row polymorphism in a language, and maybe I can't think of an obvious mainstream language that would support this, but I have this problem of wanting to switch between a record type and a variant type that has the same sort of fields in the way that it's done between concatenations and variants. So that's something to keep in mind. Maybe there's something to do with like if you could like have polymorphism or labels, but again, I think it's even less common for a language to have something like that. So implementation is also a very obvious example that arises. And how do you get performance in this implementation, in this sort of calculus that has so much like funny stuff going on in terms of indices and shapes, and how the data is stored in arrays? I think the idea for getting performance in star would end up being around erasing the subtyping, and this seems like a standard sort of procedure. If you want performance on anything that has to do with subtyping, you will need to erase subtyping to make sure that at every point you know exactly what is going to be the layout of the records that you're dealing with and what variant cases may arise. So this would end up being around monophoralization. So it's likely that you couldn't like have amazing performant code generation for like fully like for like polymorphic star code, but with like knowledge of what the specific shapes are, it should be reasonable to generate static sort of layouts for the arrays. And there's like an example process of like what these layouts might look like, where like, for instance, I'll keep track of like for concatenation shapes, I'll like keep track of like at which index does that bit of the concatenation shape start, or that component. And lastly, and I think there's a lot of sort of future like sort of ideas to explore with star. I don't think it's just like this one silly idea where you just give give something like algebraic data types for arrays and funny stuff happens. Like, go figure. I think there's like actually things to explore. And obviously one obvious thing is to look at polymorphism and what properly happens there. But also another funny thing I tend to notice when I would tell people about this is that they quickly start asking, oh great, you've got structured types, how do you get rid of them? And well, I think the answer here is to use some sort of coercion operator. So you can either try to keep it safe, you can say that this coercion operator has to work up to sort of with respecting structure. But really, it's just an operator that corresponds to reshaping. If I've got reshaping in a classical sort of array programming system, I'll take an array of some shape and then I'll reinterpret that same buffer, that same data with a different layout. And this corresponds to a very similar operation, where over time I can get rid of pieces of structure and replace them. So that's like exploring what sort of operators should be used there, and this probably will have to be done in conjunction with looking at what performant code generation should even look like, and what sort of coercions are reasonable to do in, say, constant time without like extra overhead. And I think so, and in algebraic data types fashion, it would be interesting to look at recursive shape types. I think there's interesting sort of problems that this might be able to model. And lastly, I think there's some cases where maybe this is too naive. Maybe like, sums and products, and the meaning that products and concatenations and records and variants are not sufficient for whatever you want to do. Like one obvious example that I came up with is stencils and convolutions. I think with something like filters, I think there's something reasonable you can do, that you can give it a reasonably shaped polymorphic signature. But for instance, tensor convolutions, I think you just like you sort of quickly get deferred back to integer indexing. Like it's maybe not ideal. Maybe there's some more shape types and index types that you might want to be able to use. All right, but that brings me to the conclusions. So star is this pointful array calculus that has structured array shapes and indices, so they get equipped with structural subtyping. It's kind of like algebraic data types for arrays. That's sort of my inspiration. And there's this, I think, this potential for this work, for looking at type inference, for getting performance out of it, for maybe having it in an actual proper array language as an extension of its type system. And the way I look at its importance is that it's this middle ground in the design space of array type systems. Because you've got, I think when you look at the polarization between a lot of the practical array type system, array languages being basically untyped, whether they're embedded or otherwise, versus like, the very safe but maybe a bit complex dependent types. And yeah, I think sort of lastly the argument sort of comes back to the case study, is that structured types will sort of lead you to better structured programs, because star isn't just about the types. It's about giving more structure to the values themselves, and hence sort of fixing the question. Because perhaps the question that we're asking about like typing arrays is wrong. Like maybe you just can't type sizes that way. Maybe you should make the question different. You shouldn't type sizes as parts of shapes. You should make the shapes more interesting, so there's more interesting types to give them. And yeah, that would be it. That's the finishing thought. So thank you. And I'm happy to take questions. So anyone ready? He's even got a mic.
Yeah. Very interesting. Very interesting.
Thank you.
I'm not really all current with arrays, but I'm very, very interested in Dolan's work on algebraic subtyping. So 2 questions there. First one is, you spoke a bit about. I'm not sure whether you talked about the distributive lattice, but you did mention about broadcasting as basically a join operation, right? But you didn't actually mention it as a join of the distributive lattice. So conceivably there will be a meet as well. And does that have a name?
One more thing. So it actually ends up being, because it ends up being, I really hope I didn't make typos in the slide, but it ends up being a meet. And the meet, it is actually some messy things with algebra. That's the most messy thing about the system in terms of the algebraic subtyping bit. Because having it be a meet breaks the polarity restriction in Dolan's work in certain places. And so the prototype implementation that I wrote was using Perot's extensions to avoid this problem. They was using the Boolean algebra formulation of the type language. And then you can actually have a meet of types be a result of an operation, or a result of broadcasting. As for the idea with joins, I'm afraid I do not know. I think I briefly thought about it, but I couldn't come up with a good answer. I assume it would come from like having like indices that belong in both shapes, and that would be the question of in what context you want that.
It's a join, isn't it? I mean, or do you think of it as a meet instead?
Versus a name parameter passing in functions.
Sorry,
how would you
could
comment
you repeat
on
the
that?
question? I got distracted. Could you repeat the question?
Yes,
I think there's a relation. I think there's a lot of relation between just this general idea of like.
Shall I repeat my question or not?
Sorry, I think I did. But I think there's a general relationship between like having tuples in your language versus like having records and structural record types. Do you need to write down the type definitions, or do you use things unnamed? But sorry, could you make it more specific?
Yeah, that was my question. So in function calls or function parameter passing, we have basically 2 approaches. The standard one, which is positional, and in some languages where you can alternatively or exclusively use name parameters. Yeah, and this looks a bit like the same. You give the axis a name. But my question would be, perhaps there's more, but that alone, how much does that help?
So I think that exactly corresponds to just label axes, right? Because when you just have function types which allow you to pass in keyword arguments, perhaps it more specifically corresponds to only having products and sort of tuple shapes, where they're sort of unnamed. The difference here is that we also have concatenation shapes. So I think there isn't anything obvious that corresponds to that on that side. But yeah, that's exactly what I would better to name your array axes as opposed to keeping them unnamed. It's exactly this difference between positional and keyword arguments, like in OCaml or something, or in Python.
Then what about naming the indices?
Sorry?
Instead of indexing by numbers, you could also indexing by names.
Within the array?
Yes.
That's exactly concatenation shapes. Well, like in some way, like if you recall if my slides work, then I will gladly show you. But if you recall the example with like specifying that an image has a channel dimension which is a concatenation of R, G, and B, then this is exactly, I'm just naming the 3 elements of the array, or like the possible indices. And I think that's quite convenient that I can just use names for like different parts of the array as a concatenation.
It really came out well. I had a very quick comment or question. So view shapes, view changes in PyTorch. Would those kind of operations cause problems in this calculus? I mean, when you change the view, it can match in an unintended way. I was just guessing. Or
yes, so exactly. That's also something that would have really helped if I had slides, because there was an example there. It was exactly about this idea of coercions that. Yeah, I can't show it to you.
We'll catch up. I think this was fascinating area and very important. So
thank you very much. Yeah, I'm very glad that you enjoyed it. Thank you.
Okay, thank all the speakers of this session once again. And
thank you.
That concludes the Array workshop. Let's give a big round of applause to the organizers for running such a nice workshop. First time for me to attend. Thank you.